I think you may start.
Should I start, sir?
Yes.
Sir, is it visible presentation?
Yes, yes. You are showing basically the graphs.
Yes, sir. Yes, sir. Yes, sir.
8 graphs are there.
Yes, sir. So basically, the first figure, which is in blue here. So what we have done so far, we have taken EEG data for an experiment in which 1 minute eyes were open, 1 minute eyes were closed, and so this was the experiment which was done, and we have divided into different segments. For each segment, we have found subband CRV, which is basically a feature vector for that particular frame. And now, for consecutive frames, between consecutive frames, we are finding Euclidean distance between subband CRVs or our feature vectors. So we are just finding the distance. When the first figure, which is in blue, shows here it is written P1 to 64. We have considered all 64 eigenvectors weighted with their eigenvalues, summed them all, and find the distance between them. So here we cannot see any transition if any brain state is changing or what is happening, what is the underlying dynamics. We have no information about that. So what we have done, we have taken two segments. The one is you sum all the eigenvectors from 1 to 32 here in this on y-axis it is written, and here we take 33 to 64. All these eigenvectors, the lesser dominant eigenvectors, or we can say smaller eigenvalues and corresponding eigenvectors, if you will sum. So here we can see some transition is happening. Here some transitions can be observed, but if you will see in the dominant ones, we don't see any kind of transition. So further we have divided it to small segments. So here we have taken only eigenvectors correspond 1 to 16, then we have taken from 17 to 32, then 33 to 48, and then 49 to 64. So different set of or block of eigenvectors weighted with their eigenvalues were summed, and then we just found the Euclidean distance between them. So basically we are just finding, for each frame we are finding a feature vector and finding the Euclidean distance between the previous frame. What is the distance of this feature vector from the previous frame? So this is the whole approach. So based on that, just by comparing the current feature vector or current segment CRV with the previous one, we are able, see here also we can see the dominant eigenvectors do not have any kind of brain state information, but you will see the lesser dominant one, even the other ones also. So here we have find out. So if it is lesser, the eigenvalue is lesser than 1, or if the eigenvalues which is lesser than 1, if you consider that, so they all are very small in values. So if we will consider those eigenvectors, so there you can see brain state transitions clearly. We have observed, verified with the results, that wherever these transitions are there only the person or subject was changing its brain state. So this was for this task. So we can clearly see the transition in the invariant eigenvectors as opposed to the dominant ones. Generally we consider that dominant has the information, but here we can clearly see that invariant, the least one, has the information of how your brain state is changing. So we have extended this work and also used another data set in which the both the data sets are publicly available, and the whole work is also there. Publicly available work is there, it is. So in one of the transactions, IEEE transactions, you can, if you want to go through this data set, so all the links are mentioned for referring to that particular data set. So in that paper, link is given. So here, for 5 minutes, the person was in resting state. The next 5 minutes, he was doing two tasks were there. Task one was visual task. A visual stimuli was there with concentric ring flashing at 5 kilohertz and 5 hertz. Sorry, 5 hertz. And task two was motor task, finger tapping. So either task one was getting performed or task two was performed. Then for next 5 minutes, and again the person was in resting state. Then next 5 minutes, either task one or task two was happening. So this was the complete reset. Total 25 minute was data was there, and you see sampling frequency is 5 kilohertz, which is too high. If you will process this 5 kilohertz samples per second for 25 minutes, it will be too time taking. If you will see, if you will process data for one subject, so there were total, I guess, how many subjects were there? I don't remember how many I guess around 20 or so. So for those many subjects, even for one subject, 25 minutes data, and for each second we have 5,000 samples, it will take too much time to process. So obviously here I have done down sample. I have down sampled my data to 500 only. 10 times I have down sampled because I was not interested in too high. So lesser, to reduce the complexity of my approach, we have reduced the down, we have down sampled my data here. So this, other than that, the features which we are, one thing I forgot to mention, I with in the whole pre-processing, the pre-processing, I have not done any kind of pre-processing with the EG data, because we consider that while doing filtering or any other thing, we may lose some critical information which can be necessary. So you choose features in such a way that they are very robust. The feature itself is very robust, that you are not acquiring too much information. So for all those experimentation, we have not done any kind of pre-processing other than downsampling. Here I have done downsampling here, so no filtering, nothing. So we just thought that our data is too robust, that automatically noise will get distorted, so we'll get the information. So for this data, we have done the same approach, as we have discussed, found the subband CRV for each frame and compared it with the previous one. And these are the results. We were able to find the brain state transitions. Even we can also see. So this is task 1, this is task 2, task 1, task 2. So like that, we have not extended, but this can be extended to brain computer interface. So suppose if we can characterize that this is state 1, this is state 2, this is state 3, if we can do this kind of characterization. So this was in one of the future scope, where we can characterize these brain states, and then it can be translated into command. So suppose we have defined that uh, these 4 tasks are there, which person can do, or a person. So this is the application which we have thought that it can be implemented in future. So we have not done it so far. Acquire the data, and suppose a person is having robotic arm, or he is sitting in the wheelchair, so we can tell that person that these are the 4 tasks. Maybe you can just close your fist, or maybe you can do some eye blinking, or maybe the person can do. So different type of task can be associated with different commands. So suppose we can relate that if person is doing eye blinks, or if person is just hand movement, right hand movement is there, or leg movement, any a little bit of movement is there. So you can connect that if we can identify that particular task, or we can identify or characterize that particular task from our brain signal, directly that task or that signal, that information, that state can be translated into commands, and we can move the wheelchair accordingly. So this can be one of the application. So where this taking the transition of brain states can be really helpful, where you just have the brain signals for your subject, and corresponding to different tasks, different functions of the wheelchair or any other robotic arm, or whatever machine you are operating, you are just translating your brain state into that particular command. So this is one of the application of this particular work. Now extending this how we are doing this thing, we have extended our work to real-time automated epileptic seizure detection. So how we are doing it? First of all, we thought that in the previous situation we have just seen correlation coefficient matrices. We are just finding what is the linear relation between electrode 1 and electrode 2. We are not exploring anything, but we find out that if we become very specific, what physical entity we want to capture, what is the underlying dynamics, what is the physics of the problem, if we consider all these things, so then considering that you should choose your functional connectivity matrix. We should not just directly jump to any connectivity matrix. We should be very careful that what is the application, what is the problem, what I am trying to address, what is the physics. So suppose we say seizure progression in our brain. So seizure, obviously it will be there in one particular area of my brain, and then it will progress in different parts of my brain. So it will have one source, and then it will slowly spread. So this kind of seizure will be there. So in that case, slowly from that particular point, the progression or some kind of diffusion is happening. So just if we are a little bit concerned about our problem, that some kind of diffusion is happening, so why don't we model, or why don't we use something which is related to that diffusion? So we consider that network diffusion is related to signal progression in our brain. So signal progression can be modeled as a diffusion of information, diffusion of signals in our brain. So it can also be modeled as network diffusion equation. So if we model our uh, signal progression or seizure progression using diffusion equation, so we have in my preliminaries I have discussed that network diffusion equation is there, so we can represent that. And then if we have network diffusion process, so heat kernel is the fundamental solution of network diffusion equation, which considers the overall dynamics of the underlying problem. So in that particular situation, if seizure is getting progressed, so if we just find the heat kernel, which is the fundamental solution of network diffusion equation, fundamental solution is just the basic, or which is capturing the overall dynamics of the system. So that is the fundamental solution of that network diffusion equation, which is heat kernel. So in my previous slides, we have seen that the formula was there. How do we find heat kernel for between any two signals? So channel 1 is there, channel 2 is there, two electrodes are there. How do we find heat kernel, which is basically exponential of this signal minus this signal norm, some distance, something was defined in this way. Formula is mentioned in the previous slide. So basically, in this situation, we have used heat kernel as a functional connectivity measure, because we consider that it is similar to network diffusion, and we are trying to model seizure progression in that way. So heat kernel will be the most natural phenomena which will be associated as a functional connectivity measure. And on the top of that, we find that eigenvalues and eigenvectors of heat kernel is not very too much informative. But on the other hand, if we find Laplacian of that, so Laplacian we have found. So Laplacian is basically, Laplacian is a matrix. D is the degree matrix. W is the adjacency matrix. So adjacency matrix is basically the edge weight matrix here. So in this case, we thought that we will use the heat kernel matrix as a adjacency matrix. Some people generally in the graph signal processing, if you will see, generally correlation coefficient matrix will be used as a adjacency matrix here, or edge weight matrix here. Some people uses 1010, which is if two nodes are connected, then one weight will be given. If two nodes are not connected, zero weight will be given. So depending on the situation, some people consider 1010 as a edge weight matrix, some people consider correlation coefficient. In our scenario, as we wanted to capture the diffusion phenomena, and so we consider heat kernel as a edge weight matrix. Then we find the degree matrix. Degree matrix is nothing but the weighted sum, the sum of any row sum or column sum of the edge weight matrix or adjacency matrix. That defines your degree matrix, and that's how we found the Laplacian matrix. Why we have found the Laplacian matrix? Because Laplacian, the eigenvalues and eigenvectors of Laplacian matrix are more informative compared to the heat kernel. And Laplacian is basically, Laplacian matrix is the network equivalent of Laplacian diffusion operator. And Laplacian diffusion operator, what it does, so if you use Laplacian matrix, it will tell you what is the, how the information flow, how the information is flowing between different brain electrodes. If we want to capture that, so Laplacian matrix will be a good thing. So in this situation, what we have done, the same thing in order to, I think I have covered this. One more thing I forgot to mention. So overall, in short, if I want to summarize what we have done for seizure detection, similar to the previous case, the EEG data was there. We have found the segmentation, and for each segment, I found the heat kernel. Heat kernel, like we have correlation coefficient matrix, similar to that, we can find the heat kernel. So heat kernel will tell what is the relation between any two electrodes. And once we have the heat kernel matrix with us, we have our WS, then we can form degree matrix, which is just the row sum or column sum of the heat kernel matrix. And once we have both, we can find the Laplacian matrix. So Laplacian matrix basically models the information flow, the rate of information flow between any two electrodes. And if you will see the eigenvalues and eigenvectors, so the eigenvalues and eigenvectors of Laplacian matrix are too informative. The physical meaning, the notion of spatial frequencies are related to the eigenvalues and eigenvalues of the Laplacian matrix. So it is claimed in the literature. Already literature says that eigenvalues of Laplacian matrix carries a notion of spatial frequencies. So if you will see the higher eigenvalues which is having higher values, they represent high spatial frequencies, and the eigenvalues, smaller eigenvalues of Laplacian matrix carries notion of low spatial frequency. Why we are considerate about spatial frequency in this situation? Because till now, in the previous situation, we have just thought that the brain networks are changing over a period of time. So time varying brain network. But if we will see network sensors, different sensors are placed in on different areas of your brain. So spatially also there will be something happening. So how can we capture both spatial as well as temporal information of our data? How we can incorporate both? So this situation we are, if we are considering the eigenvalues of Laplacian matrix, we are capturing the spatial information from our brain signals, and also as we are using different segments, so obviously we are also using the time varying information of our brain. So this work basically, if you use heat kernel matrix and find the Laplacian matrix, we are capturing temporal as well as spatial dynamics of our human brain under this situation. So this have been used. The smaller eigenvalues which represent low spatial frequency are smooth and vary slowly across the graph. So that gives coarse information of the brain state. What is the overall picture? So what in coarse, basically not final, not too much detailed information, but coarse information will be given by that. And eigenvectors corresponding to larger eigenvalues represent high spatial frequency, and they give more detailed information. So if one is interested in coarse information of any system, so they should look for smaller eigen values of Laplacian matrix. And if one is interested in detailed information of your brain state, you should be looking the dominant eigenvectors of your Laplacian matrix. And Laplacian matrix we have already discussed. So here also, what is the experiment? The publicly available data set, everyone knows CHB MIT scalp EG data set, which is available on PhysioNet. 23 participants were there, and number of electrodes 23, sampling rate. So some of we have the whole data is there, in which various sessions were there. In some of the session, person was suffering, the subject was suffering from seizure. They were not doing any experiment. The resting state data was collected. In resting state, sometimes in some of the session they were getting seizures, epileptic seizure, and some of the times they were not getting. So this is the result with the real time data set. So what we are doing? We are just comparing. So once we have Laplacian matrix with us, we can always find eigenvalues and eigenvectors. We can form subband CRV. In this case, we were interested in the detailed information of seizure. So we have focused on the dominant eigenvectors of Laplacian matrix. So here, if you will see, we have formed subband CRV using the dominant eigenvectors, and then we just found the Euclidean distance between consecutive subband CRV. So right side black figure shows the distance between consecutive subband CRVs when the person was not having any seizure in that period. So without seizure, this segment is there, so we cannot see any sharp transition here. But on the left side, if you will see, which is in blue, so there are three subjects data. So three different subjects. So here we can see when there is no seizure onset, so continuously the distance was having some value. But as soon as the red line shows the seizure onset and black line shows when the seizure was over. So when the seizure started, at that point we can see a sharp transition in the graph distance. Why this is happening? Because so interpretation, obviously results are there, and then we will have to interpret the data, that what it represents. So here obviously it was expected that when seizure starts, we should have some transition in the brain state. Our brain state should change significantly. The person who is suffering from the, he was normal for some period of time, and then suddenly seizure started, so the brain state should change. Ideally we should be able to capture that change also, how when it is getting changed. So once seizure starts, once seizure onset is there, at that time the different areas of our brain will be highly synchronized. So the synchronization will be maximum between between different nodes, different sensors. So maximum synchronization will be there. So in that scenario, the information flow, the rate of information flow, as we are finding the eigenvalues of Laplacian matrix. So Laplacian matrix measures what is the information flow when all the electrodes are highly synchronized. So the information flow will be minimum. So there will be no information flow between different electrodes. So network in the when seizure starts and when the seizure state is there, when the person is going through seizure, at that time maximum synchronization, no information flow. So that's why almost similar networks will be formed. And if we find the distance between two similar networks, the distance will be zero. That's why we are able to find this sudden change in the distance when seizure state is there. So clearly we can see that just by comparing current seconds data with the previous second data, we are able to track the brain state transition, how significantly the brain state is changing. But on the other hand, when he is not suffering from the seizure, so sometime he something is going on, he'll be doing some activity, he'll be talking, thinking something. So there is a change in the, there will be some distance between them. So it becomes obviously very crucial that how we are finding the distance between any two states. So here we can see that, so the application can be, what is the application of C finding just the seizure onset? So suppose nowadays portable EEG devices are there, so a person can be wearing that headset, or in maybe in hospitals, if a person is even admitted 24 hours, no one can be there with him. So when the seizure starts, continuously alarm can be there associated with that. Once we in real time we identify that seizure is there, alarm will rung, and the caretaker can attend the subject that and can provide the medicine to that patient. So like that it will be useful. So this work can further be replicated in different applications. We just wanted to make it real time. So something we have for 23 subjects, almost for all the subjects we were able to detect the seizure onset. So, based on the work so far, obviously, what we were working, what we have made subband CRV or CRV, the feature vector we have made. We have made that CRV from sometimes from Laplacian matrix, sometimes from correlation coefficient matrix. And what is that? Correlation coefficient matrix means we are considering that brain is a network in which different nodes are there, and they are having some kind of connection between them, that is defined, that is given by Laplacian matrix or correlation coefficient matrix. So basically in one frame one network is there, in as in the first application we have shown, even we have plotted the brain network in the first application. So in one scenario one network is there, in another scenario another network is there. So based on the current work only, we have proposed that why can't we use this phenomena as a graph distance between any two networks can, even other than this scenario, this all this processing, biological networks or computer networks or networks will be forming in different situations. So wherever networks are there, we can always find out the adjacency matrices or edge weight matrices of any two networks. And when we can have edge weight matrices, obviously we can find out what is the eigenvalues and associated eigenvectors. Once we have eigenvalues and eigenvectors with them, we can find the Euclidean distance between them, and that can give us the measure of how similar those two networks are or how different those two networks are. So that's how so this thing is the basically the same methodology, but we are proposing a network distance measure, that this work can also be used as a find in order to find the similarity between any two networks. So what we have done, we have compared this work with already existing works. So this is the Hemming distance. Hemming is distance is graph eddy distance, which basically finds how many structural changes are required in order to transform one network into another. So when we use, instead of, this is the result, the last one is our proposed approach. The same thing we have done, what we have done, divided the data into frames and finding subband CRV and finding the distance. So we claim that just finding subband CRV and finding Euclidean distance between them will give the how similar those two brain networks are. Instead of that, if we use existing distances, we will not be able to get those much transitions very carefully. So this was the experiment, eyes open, eye closed, that first experiment which we have already discussed, and this is the result of our proposed graph distance. But if we compare this with the existing graph distances, we see that the first is Hamming distance, which see how many net structural changes are required in order to transform one network into another. Second is matrix distance, which is just finding the norm 2 between edge-weight matrices of consecutive frames. The third is L1 distance on eigenvalues. We are finding the L1 distance on eigenvalues, L2 distance on eigenvalues, and the third is spanning tree decimalarity. So in all the situation, we can clearly see, in addition to the transition of brain state, only 7 transitions are there, 1, 2, 3, 4. So here we can clearly see all the transitions. But other than that, here if you will see some random the spikes are also there in addition to the desired result. So what these um, spikes are corresponding to, or here if you will see, some of the events are missing, and here also, but this was giving a better results. And in case of Caesar, if you will see existing graph distances, Hamming distance, metric distance, so the matrices, the edge-weight matrices are similar. Up to edge-weight matrices, everything is similar. After edge-weight matrices, what distance measure, what similarity measures between two networks you are using, that also plays a crucial role. So here if you will see, once you have framed correlation coefficient matrix or heat kernel matrix, and then finding the distance, Hamming distance between two networks, we are not able to track the Caesar onset. When you are using the matrix distance just finding, then also we were not able to track the Caesar onset. So all the existing distances were getting fail in finding the Caesar onset. But our proposed distance measure, that once you have the address matrices, you find subband CRV, and just Euclidean distance will clearly give the results. So this was the just these results were there to show the efficacy of proposed graph distance, that this particular measure can also be used as a graph distance measure, or to in order to find the similarity. So all these works which has been covered are already published in, so you can just go through that if you want to refer to anything, any data set. Also all the links are available on the for the data set. So what are the major advantages of our study? So the main thing, does not require any kind of training. So once we are not dependent on training any data, so we don't require too much data to our algorithm to work. Only 4 subject, 5 subject, 10 subjects, for every, even the first subject who is coming, for that also we can use all those algorithms, because we don't want any kind of training. The second is, in real time also we can work, because we are just using the consecutive instance data, current seconds and previous second. The third is, it has several applications in BCI, neurological disorders, resting state analysis, and so on. So in conclusion, I just wanted to say कि we have worked on different application, be it face recognition, tracking the transition of brain state, real-time seizure onset detection. So in contrast to machine learning approaches or artificial neural network approaches, which requires training, testing, too time consuming, it works in real time, and we have not used too typical or too complex things. We just use eigenvalues, eigenvectors, fundamentals, and some signal processing things. And in order to do that, we were able to do all the things. Some of the ideas which can be explored, or these are the future direction, that the first work, we can characterize the brain state. We have found the transition in the brain state, but we can also characterize our brain state. Once it is characterized, these characterized brain states can be translated into commands, and they can be hardware can be made in order to do BCI, in order to use this thing in BCI application. Using this approach, we can also explore the epilepsy diagnosis of the disease. And one new area is there these days, EEG microstate. You might have heard about this term, that microstates are there even if we are sitting like this. So some 4 or 5, generally people used to claim that 4 or 5 brain states or microstates will be there. So our brain will be continuously traveling between, or continuously moving into different brain states. So this can also be explored in future using graph theoretic approach, that what are the underlying graphs and so on. So, and nowadays graph signal processing also is a very new area, in which all the traditional signal processing approaches are getting extended into graphical domain. So these are some of the things, and some references I have also mentioned here. So if you have any questions, you can ask. Any suggestions, any questions?
To all the participants, it's a chat box. It is, you can type your questions, suggestions.
So graph signal processing is a very new area these days. All the techniques which is there in traditional signal processing, they are trying to extend into graphical domain because it is irregular. So it is not regular thing. So how you extend all the concepts in graphical domain, that is very new these days in every area, even in adaptive signal processing. If we will see, then there also how I have worked in during my postdoc. I have worked on this area that if many sensors are there, so we are moving in the world of IoT means so many sensors will be there, so many sensors everywhere, sensors will be there. So if we lose data from some of the, so obviously when so many sensors are there, some temperature sensors, some pressure sensors and different sensors, so many sensors will be there. So what if, so we can make a network of the sensors. Obviously the graph is very related to, or graph is naturally connected to different sensors. So from different sensors we can from graphs, so whatever is defined on the graphs, that can be extended to that IoT thing also. So once you have that, what if some of the data is missing from some of the sensors, so can we retrieve that data also? How do we get missing samples from that? So I was working in that domain during my postdoc. So how we can extend this in signal processing in continuous EEG data, generally what we used to do, interpolation or something will do. So how we can do that, graph Fourier transform, and how all those things are there. I was working in that domain, so that is also quite new. So where, so graphical domain, because in so many areas, if we will see computer science and everywhere nowadays, even VLSI domain also, there are so many components will be there, so they are also forming networks everywhere. Graph is coming, so all the problems are naturally associated with the network. So if something is happening on the networks, we can implement that also in our area. So that is the quite emerging domain these days.
One of our participants was he is working in IoT.
Okay.
Today, Snigdha, she is, I am not able to see her in the participant. Otherwise, she had been asking that how can we apply the GSP in the IoT.
Okay.
Can you just, if you have any worked in particular problem, can you just brief us?
I exactly I don't have the results right now with me, but what I have done, we have data. I think the data was complete. Data was temperature sensors data was there for a particular state. So different, so many sensors were there. Temperature sensor in a, I think I don't remember the country name also, but real data was available. So
Okay.
what? So from, so how many samples, we just wanted to find out how many samples are sufficient enough, or how many sensors data is sufficient enough, whether we can find the overall picture of that particular state, right? Like in signal system, what we used to do, we take for continuous EEG data is there for 1 second, we take certain samples from our EEG data, and then from certain samples we are able to reconstruct our signal back. That is the sampling theorem. We take certain samples, and from that samples we are able to get our signal back. So basically we, using that approach, what they are trying to do, so in graphical domain, if you have data from certain samples, so are we able to get the whole picture back? So how much data is sufficient enough so that we can get the whole picture? So basically sampling, how we can extend the sampling notion in the graphical domain. That was the work in that area. So it was quite good. So in that, finding that sampling theorem, like that in signal processing we used to do Fourier domain analysis, frequency sampling where we used to do in continuous time signal is like this, then we find the Fourier transform and we see how much is the maximum frequency FM, and then FM should not be greater than Fs minus FM, and then that's how we extend. So the similar concept can also be extended to graphical domain. So how much samples are sufficient in graphical domain so that we can get the whole picture of the system. So the similar, so in order to extend that in graphical domain, we have a concept called graph Fourier transform. So they were using graph Fourier transform in order to find out how much samples are sufficient enough so that we can get the whole data like that. So some things people are working in that area. All the concept sampling, filtering, Fourier transform, everything are getting extended into graphical domain these days, because that is most naturally aligned, yeah, uh, structure with all the things in all the areas these days.
So while taking your EEG data, you have basically taken three type of weights. One is your Pearson correlation coefficient. Another is basically
Heat kernel.
uh, heat
Heat.
kernel. When you heat kernel, it is I think the Gaussian weight only.
It is similar. So Gaussian kernel, the name is given, but we directly didn't take the Gaussian kernel. We just considered that what is the underlying dynamics, because seizure progression is similar to diffusion, something diffusing in our brain. So just from there, we find out what is the fundamental solution of that, and we find out that the Gaussian kernel is basically heat kernel. The heat kernel comes from the diffusion equation. Physics में we have diffusion equation और उसका कुछ fundamental solution is there. So from that model, we have extended this. So we were looking at the fundamentals, why this issue is coming and how we can address that. So randomly, we have not chosen that. We have some reasons for that, why this particular thing.
So electrode position you are taking as then a node.
Nodes, electrode positions only.
In one of your papers, I was seeing that you are saying distance, graph distance between.
Yes, sir. The last work which I was telling you, okay, that for every node network we found that subband CRV, and we just find the Euclidean distance. That is also a graph similarity index or graph distance measure between anything. So we have tried out other than this bio networks, we some random networks we have formed, and then we found that it was working there also.
So when you're taking this basically CRE, so it is basically multiplication of a scalar and a vector.
Yes, sir.
It would be norm two distance you would have
Yes, yes, sir.
taken. So here you are basically showing that the dominant some eigenvectors.
So, what as the work says that we should not always see the dominant ones. Sometimes dominant ones. So we should always be careful that what is this representing? What is the representation? Suppose correlation. So the eigenvectors has some meaning. The dominant eigenvectors represent the direction of maximum variance. The lesser dominant eigenvectors represent the directions of minimum variance.
Yes.
Minimum variance means invariance information. So similar to that Laplacian, if you will see Laplacian matrix, its dominant eigenvector represent finer details, and the lesser dominant ones represent the coarse information. So in some of the thing, when we do graph partitioning and all those applications, there we use the lesser or lesser the eigenvalues corresponding to smaller eigenvalues of Laplacian matrix. So it depends where you should choose the dominant one, where we should choose the least smaller eigenvalues. So that depends what is the physical meaning of that.
So in that context, here actually the eigenvalues, higher eigenvalues are basically representing the frequency. Eigenvalues are also
So only for
ordered in
sir
the
Laplacian, sir Laplacian,
Laplacian
for
eigenvalue.
Laplacian eigenvalues represent higher spatial frequency, but not the eigenvalues of correlation coefficient matrix doesn't represent higher spatial frequencies. So the physical meaning, which how we are creating that matrix, that also plays a crucial role.
Uh, but whenever we are taking basically this, in most of the cases, we are taking Laplacian eigenvalues.
Most of the cases because eigenvalues of Laplacian matrix are more meaningful. That's why we generally used to choose that. And then also you should choose that graph partitioning is our objective, or finding the finer details is our objective. So correspondingly, accordingly, we should look at the eigenvalues or eigenvectors.
So how have you used the graph partitioning?
I have not worked on that. I found the application that the smaller eigenvalues are getting used there in graph partitioning, and so many other applications are there. I forgot, but it is there in my paper that in which applications people are using the low spatial frequencies in graphs. People are using in different applications.
Any other question? It's a very interesting talk. This question is from someone there
Yes,
in
sir.
EG. Full graph is considered for neighborhood graph. Full consider for in EG full graph is considered or
For
neighborhood.
neighborhood graph, I didn't consider full graph. It depends if you want to consider that only dominant connections you want to consider, you can do the thresholding and make a network. Like if you want to uh, edge weight matrices, some people used to do thresholding also, that we will consider only the dominant more than 60%, and so, and some people consider the whole. So it is up to you if you want to perform the thresholding and if you want to consider the whole
I think
neighborhood.
someone
Neighbor,
wants to ask there whether should we take all the nodes or
in my work, I have considered all the nodes. I have not left any information, because maybe when we are doing thresholding, we can leave some of the important information. We don't know which one to choose and which one to give. So in we didn't have any particular key. We could have done thresholding, but we have not done that. We have considered the whole thing. Some people used to do thresholding also.
have you also taken the concept super node when you take bunch of nodes as
No,
one?
sir, that we have not done.
Because see, what happens, especially actually, and when we take, for example, this problem doesn't occur in the EEG, but when we take the spaces of transport or this temperature sensor, when many nodes are there, if you take full graph, then it's a computational problem is there,
Okay.
because it's n by n complexity.
So in that scenario, thresholding is done, or what is getting done? I don't know.
Even especially in the image also. In image also, so what did I do? Even in cases I take a part of the image. I applied it in the facial expression.
So what you used to do that in that thresholding, or what?
So, no, what did I do? Actually, the main reason where I see that the main information lies. So I picked up those reasons
Okay.
and connected those two reasons and then make a note. For example, in my case,
Okay.
facial expression, it is eyes
Okay.
reason and
Okay.
the lip reason.
I got your point. So maybe bunch of notes you have collected
Yes,
when so
yes,
many notes are there.
yes. So because main information lies here regarding expression.
So in that case scenario, we can combine those notes, nearby notes in that scenario.
Yes. So that I applied there.
No, in my scenario, maximum 64
It's
die,
yes.
60, only
It, there you are
64
not.
or 23. So that situation didn't arise in my situation. So, but in so many papers, we will see that they always define that edge weight is there, connection is there if it is more than this much distance. If it is less than certain distance, so they discard that there is no
Yes.
connection between these two
Ah,
nodes. So
threshold
always,
is
threshold will always be defined in edge weight matrices in all the papers. If we will see some threshold will be defined, if it should be more than this, then only edge will be there between two nodes, otherwise no connection. People used to consider that zero is given on for that particular
yes,
page.
absolutely. Actually, this is to make the metric sparse matrix.
Hmm.
So, any question from the AM Shah, Bharat, Devashish, Suman, if you have any more question, Gloria, Joseph. I think for any question is there. Even I,
Oh, they.
can you provide your email ID so that if somebody has a question, they may
Okay.
ask you directly.
Okay, sir. I'll write here only in the.
Yes, even you have given me, but it would be better if you would get it. So you can see the participants can see the email ID. If you have any question in the future, you can refer to it regarding the work. So one I have one question.
Means in EEG, one electrode is connected with all other nodes. It will be computational intensive. Suman, that's what we are talking about. If suppose 23 electrodes are there, so suppose 12 in some scenario 12 electrodes, 23 electrodes are there. So finding 23 is connected to all that 23 was not too like too much data. 23 by 23 matrix was there, so it was not computationally extensive in this situation. 64 is there, then also 64 by 64. This is a very small matrix size, 64 by 64 only. So it doesn't make a significant difference. But then also, if you want to make it computationally efficient, then what we can do, we can perform thresholding. See, if some of the weights are less than this, you put 0 there, so some of the nodes will be connected to other nodes. Like if you define that if correlation is less than 0.5, I'll give 0, otherwise I'll give 1. So 1 means they are connected and 0 means they are not connected. So like that we can make it. But 64 by 64, it is not. I have processed that data, it takes 1 minute or maybe lesser than that, two lesser than that. So but then also thresholding can always be applied here to make it computationally efficient. Suman, does that answer your question? Or hope you understand, hope you find it interesting. Bore nahi hua.
Suman is actually PhD research scholar. She is working under my supervision on the medical image.
Okay.
Yeah. That is her actually so fourth semester.
Okay.
So thank you, Dr. Jyoti. It's a
Thank you,
very
sir.
very intensive but
Thank you, sir.
meaningful session.
Thank you, sir. Hope कुछ someone can take some suggestions or some thoughts or ideas from this. It
No, no,
should.
definitely your work basically, as you have mentioned it, that the in neuroscience, how it can the GSP concept be extended easy and this way, actually that will help a lot. Even I have briefed them about the basics of GSP. So in that line, it will really complement it.
Yes, sir. GSP is in recent, everything is
Yes,
revolving around GSP. Every area, wherever we see, even
yes,
I came to know that VLSI people are also moving in
yes,
GSP
yes, yes,
everywhere. So
yes, yes.
GSP is in trend these days.
So see, fundamental of GSP is very strong. That whole is more than the sum of the parts.
Mm.
That interconnection.
And obviously, all the problems are can be transformed into graphical domain.
Yes,
That's why
yes,
GSP
absolutely,
in regular
absolutely.
domain.
That
Yes.
is there. So
Okay,
thank
sir.
you.
Thank you so much, sir. Thank you, everyone.
Okay, okay. So
Okay, thank you so much.
leave. So we will meet participant. We will meet tomorrow. See, from 1:30 to 5:30, we have session. That is basically based upon the EEG from the industry person, Dr. Geetanjali Srivastav. So we will meet there. So please note tomorrow's session is from 1:30 to 5:30. Right? Please there it's because it's Sunday, so we have taken in all the 4 hours together. In between, we will have the gap. Thank you all. And you will have the quiz on the Monday. So be ready. Whatever the slides have been provided, based upon it, it will be there. Whatever the material has been provided, that will be the base one. Wish you all the best. Thank you.